So you have a complex class till 3:30?
Yes, ma'am.
Yes, ma'am.
Okay. All right. So in the last lectures, we saw the methods to find the approximate solution of the initial value problems. So basically, we considered the first order differential equation together with the initial condition, right? And we learned that how do we find the approximate solution of this initial value problem. So now, see, we have learned the methods for this one particular problem, or it's a class of problem, you can say, the first order initial value problems. But you can extend these methods to the system of the differential equation, the first order differential equations, and also for the higher order differential equations, right? Because let's see, how will you do that, right? So we just have to see that can we translate the given system of differential equation in this form, right? Then suitably, the methods which we have learned, they can be expanded to the system of the first order differential equations together with the initial conditions. Okay? So let's consider the system of these. Okay, so I'm going to consider the M differential equations here, and the variables which I'm using here is a y1, y2 up to yn. Okay, so the first differential equation is y1 prime. This equals, so this is a coupled system. So I have a f1 which depends on x, y1, y2 up to yn. Okay, and the corresponding initial condition I'm going to have it. So let me write down all the differential equations and then I will write down the initial conditions. And the second equation, I'm going to have it as y2 prime x. This equals f2 x y1 y2 up to ym, right? And the mth differential equation, which is in terms of the variable ym, it is ym prime equals a function fm, which is a function of x, y1, y2 up to ym. Okay, and we have a corresponding initial condition. So y1 at x naught equals, let's call it y1 0, y2 at x naught equals y2 0, and ym at x naught, this equals, let's call it ym 0. Okay, so this is a system of M first order these differential equations. Okay, so together with the initial conditions. All right, so if you introduce this new variable, let's define capital Y as this vector. So I'm taking this as the vector of length m, and each component is going to be, so the components of this vector are going to be y1, y2 up to ym. Right? And if I define the function f, which is going to depend on, so let me use small y still. Okay, so which is going to depend on x and all the these components y1, y2 up to ym, right? So basically I'm going to write that because I'm defining y as these components together, so I can write this is a function of x and y, and this I'm taking it as f1 of xy, f2 of xy, and up to fm of xy. Now it just that because this functions depends on the component on these variables y1, y2 up to ym, right? And I altogether I've defined it as y, so that's why I'm writing it as the in place of writing y1, y2 up to yn, I'm just writing that they are the function of x and y. Okay. And if I didn't denote this initial vector as y0, so I'm just trying to be consistent with the notations which we have used for this differential equation. So let's call it y1 0, y2 0 up to yn 0. Okay, so then this system, if we call it as, so let's call this is 1 and this is 2. So then we can rewrite 2 as so we can write it as y prime x. So you can see that I have the, if I try to write down this in the form of the vector, so I will get this as y prime x equals f of xy with the initial condition as y at x0 equals y0. Okay, so you can see that we have got, we could reduce this system of differential equation in this form. Okay, only thing is to keep in mind that now y and f and y0, they all are vectors here. Okay, so now the methods which we have learned, they can be suitably extended for this vector setting. Okay, so I'm not going to discuss them, how these methods are going to change, but I just wanted to give you the idea that, you know, even you have to do, suppose you have to understand the numerical methods for the system of the differential equation. Whatever we have learned, those methods can be suitably extended to the system of the differential equations as well. Okay, so for example, Euler's, modified Euler's, Runge-Kutta methods. So they all can be extended to the system of the differential equations. So now let's look back the higher order differential equations. Okay, suppose we have so say I have the mth order differential equations. So I'm considering the mth derivative of the y, this equals, so this is a function which is going to depend on x, y, y prime up to m minus 1th derivative of y. Okay, and together with this, I will have the initial conditions as y at x0, this equals, let's call it, so let me use this notation y0, okay, and so I'm using the capital Y here, and y prime at x0, this is equal to y1, and up to y m minus 1, m minus 1th derivative of y at x0 is given to be y m minus 1. Okay. So if we have this, how do we reduce this into the first order system? Can you tell me? So can you, suppose I want to reduce this problem into a system of differential equation. So what I should do if I want to reduce, say, for example, let's take the case of the second order differential equation. Can you write down in terms of a system of the first order differential equations, what we are supposed to do?
Yes, ma'am. Ma'am, here, ma'am, ym minus 1 x naught equal to ym minus 1, then derivative both side, then y dash equal to y to the power m x naught. Put LHS and in RHS f of x comma y1 y2 dot dot ym minus 1.
Right, so you have to introduce a new set of variables. So let me change the notation here because this is not, we're defining the initial data. So let me just take y0 and then take the subscript. So y0 and then y0 let me call it 1, and this is m minus 1. Okay, so that it's understood that the y naught is basically referring to the initial data. All right, so now what I'm going to do to reduce this into a system of the differential equations, I'm going to introduce this new set of variables. So I'm going to define y1 as y, okay, y2 as y prime, y3 as y double prime, and up to ym I'll define as m minus 1 its derivative of y. Okay, so using this, you can see that if I take the first differential equation is going to be, if I take the derivative of the y1, this is going to be y prime, and y prime we know that is y2, right? So this is y2. Now if you take the y2, the derivative of the y2, this is going to be y double prime, and y double prime is y3. Okay, so you get this as y3. So likewise, if you take the m minus 1th derivative, sorry, m minus 1th component here, that is ym minus 1. If you will take the derivative of this, you will get ym. Okay. And lastly, when you take the derivative of the ym, it is going to be mth derivative of the y. And mth derivative of the y is given by this equation. Right? So I'm going to get this as f, and it is a function of x, y prime up to the m minus 1th derivative of y. Now we know that y is y1, y prime is y2, and m minus 1th derivative of y is ym. So this f is going to be a function of y1, y2 up to ym. Okay, and let's see how the initial conditions reduces to. So first condition is y at x naught is y naught. This means that y is y1. So we have y1 at x naught. This equals y naught. Okay. Second condition is y prime at x naught is y naught 1, and y prime is y2. So this is y2 at x naught. This equals y naught 1. Right. Likewise, we are going to have this as ym minus 1 at x naught. This is equal to y0 sorry, let me just be consistent. So this is 0 is below and 1 is above. Okay, so this will be 0, m minus 2, and finally ym at x naught is going to be y0, m minus 1. Okay, so basically you could reduce the system of the differential equation, sorry, the mth order differential equation into a system of m first order differential equations, right? And we have already seen that the system of differential equation can further be reduced to a in this form, right? So you can define suitably f at y. Let me use a capital Y here. Y as y1, y2 up to ym, right? And you can try to observe that I can write this as capital Yx prime equals. So try to observe the right hand side. So you, okay, so first let me write in terms of the y1, y2, ym itself, and then we can write down in terms of the capital Y. So you can write down this in the matrix form in this way. Okay, so you will not be able to, you need, once you have the form of the f, you will be able to write down in terms of the matrix form, because we need a linearity to write this. Let me not go into that. So let me directly use the F1, F2, and Fm here. So this is my F1, okay, and this is F1, which depends on X and capital Y, where capital Y I'm defining it as Y1, Y2 up to Yn. And this is F2, this is Fm minus 1, and finally this is Fm. So then I can write the system as Y prime equals F of xy, right? With the initial vector y naught, so let me use a little change of notation. So with this, let me start with the 0. So I will be able to define y naught as this vector y0, 0, y0, 1 up to y0 m minus 1. Okay, so I can write the initial condition as y at x naught equals y naught. So again, you could reduce a mth order differential equation into this form, which basically looks again, it's the same form what we have here, right? And this methods which we have applied here, which we learned here, they can be extended to the system of the differential equations, and thereby they can you can use those methods to apply even for the higher order differential equations. Okay. So now what we are going to learn is that so far we have discussed only the initial conditions, right? The differential equation together with the initial condition. So basically the initial value problems. So now we are going to see the boundary value problems. Okay. So what is the difference between initial value problem and the boundary value problems? So you can see in the initial conditions, the data is prescribed only at the initial point, or at, you can say, at one point, right? Even if you see the system, there also you will see that each of the variable is prescribed at the initial point, which is x naught, right? And when you have this higher order differential equation as well, you can observe that the y and it's all the derivatives up to m minus 1, they're all prescribed at the one point, x naught, okay? But in the boundary value problems, the unknown solution, which is y, this is prescribed at more than one point, okay? So let's consider boundary value problems. So as he explained, let me just write it down. So in initial value problems, the conditions on the solution of differential equation, they are specified at a single point, which is called the initial point. Okay. So what we are going to consider now? So we are going to consider the case where we have the unknown solution is prescribed at more than one point. So when I write unknown solution, this is the solution of the differential equation, right? Together with the conditions which we will have. So basically, let me write it. So in which the solution of the unknown solution has conditions imposed on it at more than 1 point. Okay, and such differential equations together with the conditions, they are called the boundary value problems. And we are going to use the shortened notation for the boundary value problem as VVP. All right. So in particular, I'm just going to consider the boundary value problem, this specific boundary value problem. So this is a second order differential equation. So d2 by dx squared. This equals f, which is a function of x, and it can depend on y and the first derivative of y. And let's call that x is belonging to some interval AB. Okay. And the boundary conditions are y at a equals ya and y at b equals yb. Okay. So this differential equation together with these conditions, this is known as the boundary value problem. And these conditions, they are known as the boundary conditions. Right? And the name is coming with the fact that it usually happens that you are basically prescribing the values at the two endpoints, right? So basically the boundary. So that's how you're calling these conditions as the boundary conditions. Now, what is our interest? So we want to find the numerical methods to approximate the solution of this boundary value problem. Okay, so let's give it a question number. So let's call this 1 and this 2. And excuse me. What we are going to assume that this problem has a unique solution. Okay, so we assume that this boundary value problem, which is given by 1 plus 2, this has a unique solution. So you can refer to the book by the Keller on the differential equations, right? Or you can refer to any book on the ordinary differential equations to see what under what conditions you will have the existence and uniqueness of the solution for this problem. Okay, so I'm just going to state the theorem, which basically ensures the existence and uniqueness. But you can refer to more details for this book or any other book on the theory of the ODE. So this theorem says that suppose the function f, which we have here in the differential equation, if it is a continuous function on D, which is, so we can see that f depends on the three variable x, y, and y prime. So here y prime, they are in R, and x is in the interval AB. Okay, and the partial derivatives fy and fy prime, they exist and they are continuous on D. Further, consider the partial derivative of f with respect to y, okay, that is if we consider fy, if this is strictly positive for all these points belonging to D, and second condition we require is that the partial derivative of f with respect to y prime, that is the third variable, third argument of the function f, if it is bounded, then the boundary value problem, which is given by 1 plus 2, this has a unique solution. Okay, so I'm not going to go into the details of the proof, etc. So you can check out the books on the theory of ODEs. So what we are interested in the numerical method. Okay, so we have the exact solution of this differential equation, which is y, and we want to find the approximate solution of that. But the idea remains the same as we have in the case of the initial value problems, that when we say the numerical method, we will be finding the approximate value of y at the discrete points xi. Okay, so basically we will be finding the yi's. Okay, so the method which we are going to learn is the finite difference method. Okay, so basically what we are going to do in the finite difference method, you see in this problem, let's look at the differential equation. So we have the second derivative coming here and the first derivative coming here, right? So we will be basically approximating these derivatives suitably, and that will give us the method, the numerical method. So as we have seen in the case of the initial value problems as well, that the first step is to discretize the domain, right? So we have the domain AB. So we are going to discretize it into subintervals. So we are going to write AB as, so we start with x0 and then x1, x2, and this we are going to call it as xn. So I'm going to write AB as x0, x1, union x1, x2, up to xn minus 1, x. Okay, and here I'm taking the A as x0 and x1, x2, they all are going to be, they're going to follow this order. Okay, so we have a n subintervals. So h is going to be the length of each subintervals, which I'm taking equally spaced points. So it is going to be b minus a divided by n. So h's here are going to be a plus jh. Okay. What we have to do now, so the aim is that, okay, we want to find the approximation of y at each point x size, right? Suppose I have to finally reach, so basically I'll be interested in finding the y, say at xn. So to reach here, you have to find y at each of the x size, right? So how do we do it? So we are again going to use the Taylor's expansion so that we can get the approximation of first derivative and the second derivative, and then we are going to substitute this in this equation 1. Okay, so let's use the Taylor's expansion. So using Taylor's theorem, so first let's try to find that what is the approximation we can find for the second derivative and the first derivative without really using these x size. Let's try to see it in terms of the any x. Okay, so if we expand say y of x plus h, because you can see here that If you're at x0, you will use this information to find the values at the y at x1, right? That's what we did in the previous case. So basically, we have to find the approximation of y at any of the xi's. And any of the xi's, you see that they are in the form a plus jh. Okay, so I'm just taking any point x and I'm just trying to expand this term, and so that I have everything in terms of the a plus h or a minus h. Sorry, the x not any xi plus h or any xi minus h, because my points are in that way. So if I expand this using the Taylor's theorem, so this is yx plus h times y prime x plus h square by 2 y double prime x, right? And then let me put one more term. So I'm assuming that y is sufficiently differentiable. Okay, so h cubed divided by 6 y triple prime x. And let me not exactly end here. So I'll see where to end. Okay, so that you can also get a feel that how I'm ending the series. So I'm not putting a final term here, the remainder term. So I'll try to first obtain the approximation. For example, I want to get the approximation of the y prime, sorry, y double prime and y prime. So I'll see suitably where to end the series. And then we have yx minus h times y prime x plus h square by 2 y double prime x minus h cubed by 6 y triple prime x plus, so this continues. Okay. So the first thing what I want to see is that what is the approximation of the y double prime which I can get from here. So you can see that if I add yx plus h and yx minus h, right? So you will see the cancellation of this term here. Okay, and to find the approximation of the y double prime, but you will have 2 yx sitting here, right? So I'm just taking minus 2 yx, right? And complete thing, I'm dividing it by h square because I have the coefficient of the h square sitting here. Because when you will add these two terms, you will have h square by 2 from here and h square by 2 coming from here. So it will be h square times y double prime. Okay, so you can see this, you're going to get the approximation of the y double prime of x. And what is where I have to, what is going to be the order of the error here? So note that this, because of this minus sign, plus and minus alternate, different, we have the like same components, but a different sign here. So this term is going to cancel out. Okay, so I will get the remainder term of order h raised to power 4, right? Here as well and here as well. Okay, and that is getting divided by h square. So basically, I will have the remainder term of order h square. Okay. So I got the approximation of y double prime, which where I have the remainder term of order h square. So the next, we also have to find the approximation of y prime. Now, since I'm going to substitute this these derivatives ideas here, right, in the differential equation. So I want my y double prime, like all the derivatives to have the same order of the remainder term. That is for y prime also, I would like to have the approximation for, so that I can have the remainder term, which is going to be of order h square. Okay. And from these two expressions, you can again observe that I want the approximation of the y prime, right? So first of all, I cannot add them because adding them is going to cancel out this term. So I'm just going to subtract them. If you subtract them, so you will get yx will be cancelling out, and then you will have 2h times y prime of the x plus h square times this, right? So let's add both of them. Sorry, subtract both of them. Y So if you subtract yx plus h minus yx minus h, the first term cancels out. Second term is going to give you the 2h times y prime x. And when you're subtracting, the third term will cancel out. Okay. And then you will get h cube divided by 3 into y triple prime x, right? So everything I'm going to divide it by 2h. Okay, so this is going to give me y prime x. And then what is the order of the remainder term I'm going to get? So this is going to be h square, because this is h cube and then I'm dividing by 2h, right? So the one h will be cancelling out, so I'll be left with the order h square. So these are the approximation of the y double prime and y prime we can use. That is, if I want to see the approximation of the y double prime, I'll just take this factor, right? And if I want to see the approximation of the y prime, I'll just take this factor, right? For taking out the error term. So now this I have to do for each of the xi's, right? So using this, I can find the approximation of the y double prime and y prime at each of the xi's, right? So if we take now till which point I can go, right? What can be the last value of the I here? Suppose I want to find the approximation of y double prime of xi using this formula, right? You can see I'm starting from 1, not starting from 0, because you see I'm having xi, I'll be having xi minus h, right? So the minimum I can have the value of the I is 1, right? Because I'm having the data from x0, y0. And what is the last value I can have for the I? Tell me.
I minus 1, ma'am.
Right?
Minus 1.
N minus 1, because you see we have the last index is n, right? And here you can see that you have x plus h is also sitting here, right? So you will have xi plus h is also there. So basically this is going to be y excuse me, y at xi plus 1 minus, sorry, plus, so let me keep this 2yx before. So this is 2y at xi plus y at xi minus 1 divided by h square, okay, plus order h square. And likewise, I can have the approximation of y prime at xi. So this is y at xi plus 1 minus y at xi minus 1 divided by 2h. Okay, so let's give them the equation number. So we have 3 and then 4. I think we named them 1 and 2. Yeah. All right, so once we have these approximations, I can use this. So I'm going to use this in the given differential equation to design the numerical method, which is this one, right? So we have y double prime equals f of x y prime, and with this condition. Okay. So now let me write what is the numerical method we are going to get. So this in view of 3 and 4, so what we have, just write down the differential equation. We have y double prime equals f of x y prime, with y at a equals ya and y at b equals yb. Okay, so the first observation you can make that y at a, is nothing but y at x naught. Okay, and y at b is nothing but y at b is xn. Okay, so these data are given to you. All right, so this you keep in mind. Now I'm going to use the 3 and 4 to write down the numerical method. So I'm using the approximation of the y prime using this 3. This is yi plus 1 minus 2yi plus yi minus 1 divided by h square. This equals f. X will be xi. So this I'm writing at the point xi. Okay, so everything in the point xi. So this is going to be yi, and y prime at xi is yi plus 1 minus yi minus 1 divided by 2h. Okay, and I is ranging from y1 up to n minus 1. So let's call this as 5. So how many unknowns we have total? So if you see here, I have the point n plus 1 points, right? x0, x1 up to xn. So total n plus 1 points. So correspondingly, if I see that I have y0, y1 up to yn. So these are total n plus 1 unknowns. Now, how many conditions, how many equations we get from this equation number 5? So we are having the range for the I as n1 to n minus 1, right? So we are going to get n minus equations from equation number 5. Okay, so we have n plus 1 unknowns. And if you want to solve for them, we need n plus 1 equations, right? But so far we could get only n minus 1 equations. So how do we get the 2 more equations? So we use this boundary conditions. All right. So what we have got here, this system. So this is a system of n minus 1 nonlinear equations in n plus 1 unknowns y0, y1 up to yn. Okay, and we need 2 more conditions. And they're going to come from the boundary conditions. Okay, so this I'm referring for the boundary conditions. So basically, we impose them explicitly. So we take y0 as ya, okay, and yn as by b. All right. So now you can see that we have n minus 1 equations from here, and then 2 equations we have got from here. So we have n plus 1 unknowns and n plus 1 equations, right? So we will be able to solve for yi's, where I is ranging from 1 to 0 to n. Okay. So since I consider the general f here, so I cannot really simplify the things and write down that what matrix etc. you are going to get. But let me take one particular form of the f and try to and just try to get more insight about the things. Okay, so just for the simplicity, let's consider the following form of the f. So I'm considering this differential equation. So basically f, I'm taking it as px times, so I'm considering the linear function here. So px times y prime x plus qx times yx plus rx. Okay, and this is in the interval AB. And boundary conditions are y at A is YA and y at B is YB. All right, so let's call this as 6. So if you just try to compare with this given initial value problem 1 and 2, I've just taken the particular form of the f here. All right. And I'm going to assume that we have a unique solution for. Okay, so let me just take the requirements on PQR. So P, Q, and R, these I'm taking it as continuous functions on AB. Okay, and we are further going to assume that that this boundary value problem, which is 6, this has a unique solution. Okay, and what we are interested in the numerical solution. So again, the same idea that we are going to use 3 and 4 to get the approximation of this boundary value problem. So using 3 and 4, so we can get that. Let's look at the differential equation in 6. So we have yi plus 1 minus 2yi plus yi minus 1 divided by h square. And in the right hand side, this is going to be p at xi. So let me denote p at xi as pi. Okay, q at xi as qi, and r at xi as ri. So we'll have pi, and then yi plus 1 minus yi minus 1 divided by 2h plus qi times yi plus ri. Okay, and I is going to range from 1 to n minus 1. All right. So here, if you have to really see that what is the system we have to solve. Okay, so I just have to collect all the coefficients of each of the variables. So here I have ya plus 1 sitting here and ya plus 1 sitting in the right hand side as well. So I can simplify this. So let's take out the coefficients, take out the term with the yi plus 1 and ya minus 1 and yi to the left hand side. So let's write down the coefficient of yi minus 1 first. So what is the coefficient I'm going to get for y minus 1? So I have so let me take out the factor h square as well. Okay, so I will get this as 1 plus h by 2 into pi. Okay, and then let's see the coefficient of yi divided by h square. So this is going to be 2 plus h square times qi. Okay, and finally let's see the coefficient of yi plus 1 divided by h square. So for this as well, we are going to get h by 2 pi minus 1. Okay, and this equals, so I'm keeping, so note that basically I've taken this term to this side, okay, and ri I'm taking to the other side. So this will be minus ri. So, or I can write this as minus 1 plus h by 2 pi yi minus 1 plus 2 plus h square qi yi plus h by 2 pi minus 1 yi plus 1. This equals minus h square ri. Okay, and I is ranging from 1 up to n minus 1. All right. So this system, I'm saying system again and again because when you substitute I is equal to 1 to n minus 1, you will get n minus 1 equations, right? So this is not just one equation, this is a system of the equations, right? So this system, so let's give it a equation number again. 5, 6, 6, this is 7. Okay, so this system 7 together with boundary conditions y0 equals ya and yn equals by b, this forms n plus 1 equations in n plus 1 unknowns, right? So we have n plus 1, total n plus 1 unknowns and total n plus 1 equations now. Okay, so we can solve for, we can write down it in the matrix form and solve for it. All right. So, but note that since we know y0 and yn explicitly, so we can basically take them out from these equations and put it in the right hand side, right? So y0 is going to appear only when we will have I is equal to 1. All right. And yn will appear when I will have the last value of the I, which is n minus 1. So for these two equations, I can further do a step of the simplification that I can substitute these values of the y0 and yn and get a reduced system of equation. So since
n plus 1 unknowns.
Sorry, what I wrote, forms n plus 1 equation and n plus 1 unknowns. Thank you. Okay, so let's do that. So since the values of y0 and yn, they are known explicitly, so we can eliminate them from this system of equations, which is 7, right? So if we take y0 equal to ya, I can use this in this, sorry, what is that? Not the equation. So we can take y0 equal to ya with I equals 1 in 7. So what I will get, it will be minus 1. So note that if I take I is equal to 1, I will get y0 as here, right? So I'm taking this complete term to the right hand side. So the term which will consist of this will be y1 and y2 because I'm taking I is equal to 1. So the first term is going to be, so this term with the y0 will go to the right hand side. So I will have 2 plus h square q1 y1 plus h by 2 p1 minus 1 y2. This equals minus h square r1. And this term will go to the right hand side. So I will have plus 1 plus h by 2 p1 times y0. And y0 is ya. So this is going to be ya. All right. So let's call this 8. And then if we take I is equal to n minus 1, in this equation 7, so what I will get? So when we take n minus 1, the last entry, that will going to yield yn. Okay, so this term I'm going to take it to the right hand side for I is equal to n minus 1. So the first term is going to be minus 1 plus h by 2 Pn minus 1, and then we have yn minus 2 plus 2 plus h square qn minus 1, and then I have yn minus 1, and this term goes to the other side, so I will have minus h square rn minus 1 plus, so this will be going to other side, so we'll have minus sign, so I'm writing plus, so I have to take a minus sign inside, so this is 1 minus h by 2 Pn n minus 1 times yv. Okay, so the first and last equation will be reduced to these 8 and 9 in the system 7. Okay, so now basically you see the reduced system, you have n minus 1 equations and n minus 1 unknowns. All right. So what is the, so now let's write down in the form of the, in the matrix form, this system 7. So now in the reduced system, we have n minus 1 unknowns with n minus 1 equations. Okay, and which is basically I can write it, which can be rewritten as so this I can write it as AY equals B, where the matrix A is going to be, so let me define it here first A. So let's write down. So vector y will be, let me write this first so that we can just write down the coefficients, corresponding coefficients. So we will have it up to y1, y2 up to yn minus 1. So this is going to be y1, y2 up to yn minus 1. So the corresponding matrix is going to be, so let's write down the coefficient from the first equation. So the first equation is this. So I will have the coefficient of y1 as 2 plus h squared q1. The coefficient of y2 is h by 2 p1 minus 1, and rest all the coefficients are 0. Okay, so I'm not writing them. And if I talk about the second equation, so second equation is going to be the same what we have here for I is equal to 2. So I have a coefficient of ya minus 1, ya and ya plus 1 for I is equal to 2. So basically I will have it as minus 1 plus h by 2 p2, and then here I'm going to have 2 plus h squared q2, and then here I will have h by 2 p2 minus 1. Okay, and this will get repeated. So you will have the three coefficients in each equation, right? Now let me write the last two equations. So the last two equations, basically we are going to get the last three entries are going to be minus 1 plus h by 2 en minus 2 and 2 plus h square qn minus 2 and h by 2 pn minus 2 minus 1. Okay, and the last row is going to be this equation number 9, right? So I have the coefficient of yn minus 2 and yn minus 1 only. So I'll be getting it as minus 1 plus h by 2 pn minus 1 and then 2 plus h square qn minus 1. Okay, so this is the matrix I get it. But it rest all the entries are 0. Okay, and what is the vector b? So b is nothing but the right hand side. So you can see in the first equation, the right hand side is this. And the last equation, the right hand side is this. Rest all the equations, right hand side will be minus h square ri. So the first is minus h square r1 plus 1 plus h by 2 p1 times ya, and then minus h square r2. Likewise, the last two equations are going to be, so they are corresponding to minus h square rn minus 2 and minus h square rn minus 1. And then we have this term plus 1 minus h by 2 pn minus 1 times by v. Okay, so if I name this 10, so you can see this system of, so basically this matrix which you get in the system of differential equation, this is basically tridiagonal. Okay, so you can see that you will have one main diagonal, right? And then one upper diagonal and one lower diagonal, and rest all the entries are 0. Okay, so this A matrix which you get here, this is a tridiagonal matrix. And in the next section, that is, I'll see whether I can start today, or if not, then we'll be starting in the next class. So we'll see that that how do we solve the system of the linear equations. Okay, so we'll basically seeing the numerical methods for that as well. So there's one method which we will learn is the Gauss elimination method, which you might already be knowing it. Okay, so this system can very well be solved using Gauss elimination or any of the direct methods, you know it. So this can be, because of this tridiagonal structure, it can be easily solved. So this can be solved easily, say by if you use Gauss elimination. So if you're not familiar, we'll discuss it. I'm not sure if we can start today, but if not, then we'll start it in the next class. We'll learn this method, what is a Gaussian elimination. Okay, or any of the methods which you know to solve the system of the different equations. All right. So we have got a numerical method, so we can also see what is going to be the truncation error, right? So let's write down the truncation error. Let's denote it by tau, and what it is going to be. Let's look at this equation. Right, this is the main equation, we have it. So what we have to do to find the truncation error, can you tell me? If this is the numerical method, what is going to be the truncation error? So basically, I just have to see if I try to take this method as in terms of the, say, exact solution, right? So you have this equality. So if we take, which means that if you subtract this complete term, this is equal to 0, right? Now, if we try to see this complete term with respect to the exact solution, that is not going to be 0, right? So that will yield some error. And that error is basically your truncation error. Okay, so let's write it down. So we have, this is going to be y at xi plus 1 minus 2y at xi plus y at xi minus 1 divided by h square minus we have pi times y at xi plus 1 minus y at xi minus 1 divided by 2h minus q y at xi minus ri, right? So if you see this quantity with respect to the discrete solution, then you know that this is 0, right? But with respect to the exact solution, this is not going to be 0. So we can further simplify this because we know that this term qxi q into y minus r qi, sorry, qi times y at xi minus ri, this I can use it from the differential equation. So what is the differential equation? Y double prime, this equals, so we have named the equation number, right? So what is the equation number we have given? 6. So we have this as py prime plus qy plus r, right? So qy plus r equals y double prime minus py prime, right? So I can rewrite this as, this is yxi plus 1 minus 2yxi plus y at xi minus 1 divided by h square. And this, what I'll substitute here, I'm going to substitute for this term as, this is going to be y double prime at xi minus p times y prime at xi, right? This term. Let me write this little below. This I can talk and be written as y at xi plus 1 minus 2y at xi plus y at xi minus 1 divided by h square. So this y double prime I'm taking with this term. So this is y double prime xi, right? And then I have this term minus pi times y at xi plus 1 minus y at xi minus 1 divided by 2h. And this this term I'm combining with this here, pi. So this is going to be minus y prime xi. Okay, and you can further simplify this, and like, because you can already, you have the Taylor's theorem, you've already done the expansion in terms of these coefficients, right? So you can exactly find these terms using the Taylor's theorem. We have already done the expansion, but we did not write explicitly the remainder term, right? But you can write down the remainder term explicitly, and upon simplifying, you will get that. So you do the simplification. So what we will get h square by 12, fourth derivative of y at xi plus 2 pi times the third derivative of y at xi plus order h raised to power 4. That is, I've just written the coefficient of h square, what you will have from the Taylor series expansion, and this is what you're going to get. Okay, so you can see that the truncation error is of order h square, because the rest all the terms are of higher order. Okay, so this you can verify. So one more thing you can observe here, that to have this numerical methods of order h square, you need that the solution is 4 times continuously differentiable. Okay, so whenever you work with this numerical method, you always have to assume that the solution has some additional smoothness. All right. Now let's take one example and really see that how do we really solve these problems. So let's take one example. Suppose we have to solve d2y by dx squared minus y, this equals 0, with y at 0 equals 0 and y at 2 is given to be 3 point, let me write 62686. Okay, so you have to solve this boundary value problem. All right, and you have to use the finite difference method because I've just discussed one method, so it understood that what we have to use. So let's write down that what is the finite difference scheme for this differential equation. So the finite difference approximation so I'll be approximating this y yi plus 1 minus 2 yi plus yi minus 1 divided by h squared, and this is simply yi, this equals 0. And here I have let me prescribe that what h we have to take, right? Because that will give you that idea that how many I, what is the range of the I. Okay, so let me take h to be, so h is equal to 0.5. All right, so basically we have 0 because one end is 0 and the other is 2. So we are going to have how many points? So this is 0.5, 3 points, right? So 0.5 and then 1, and then 1.5 and then 2. So this is x0, x1, x2, x3, and this is x4. So I is going to range here from 1 to 3, as n is equal to 4 here. Okay, and the data which we have from the boundary, for the boundary conditions, we have that y0 is given to be, so this is your ya, so this is 0, and y2 is your yn, which is y4, is given to be y at 2. So if you write down, so this is 3.62686. Okay, so let's write it down explicitly what these equations are by substituting I is equal to 1, 2, 3. Okay, so h is 1 by 2. So h is 1 by h square is going to be 4. So this is going to be 4. So I'm just writing this equation here. 4i plus 1 minus 2 yi plus yi minus 1 minus yi. This equals 0 for I equals 1, 2, 3. So let's take I is equal to 1. So the first equation, I'm going to get it as 4 times y0 minus 2 y1 plus, okay, sorry. So I'm writing yi plus 1 first, right? Okay, so this will be by 2. Plus y0 minus y1, this is equal to 0. The second equation, when you take I is equal to 2, so we will get this as by 3 minus 2 by 2 plus y1 minus y2, this is equal to 0. And the last equation, which you will take I is equal to 3, So we will get this as y4 minus 2 by 3 plus y2 minus y3. This is equal to 0. Okay, and we are knowing the values of the y0 and y4, right? So we are going to substitute them. Y0 is given to be 0 and y4 is 3.62686, right? So this will give us the following. So I'm just going to eliminate y0 from this equation and y4 from this equation. So we get the first equation as, so I'm just going to write down upon what we get upon simplifying. So you have minus 8 y1 here and minus y1 here. So we'll get minus 9 y1 plus 4 y2. This equals 0. The second equation will remain as it is. So 4 y1 minus 9 y2 plus 4 y3. This equals 0. And from the last equation, y4 will go to the right hand side. So we will get 4 y2 minus 9 by 3. This equals, so upon simplification, we are going to get, let me write the number. So this is minus 14.50744. Okay, this is upon simplification, you will get this equation, right? So you can see here that you have 3 unknowns and 3 equations, right? So you can write this in the matrix form, minus 4, 9, 9 minus 9, 4, 0, 4 minus 9, 4, 0, 4 minus 9 times y1 by 2 by 3. This equals 0, 0 minus 14.50744. Okay, so this is a 3 by 3 system of equations and you can easily solve it. So the solution is going to be y1 is going to be this, you can verify that y1 will come out to be 0.5264, y2 will be 1.18428, y3 is 2.13829. Okay, so this is basically the approximation of y at 0.5. This is the approximation of y at 1, and this is the approximation of y at 1.5. Okay, and just to let you know that if the solving these systems, of course, manually it can be like you have to see either you have to apply this Cramer's rule, etc., and then so there are various ways to solve the 3 by 3 systems, right? But in the computer, there's a command called slash, right? The backward slash. That is, if you provide the matrix A and you provide the vector B, if you have to solve Ax is equal to B. Okay, so you just supply the matrix A and then supply the vector B, and you use this backward slash. So this is in the MATLAB. So this basically returns you this vector X. All right. So this basically this performs various combinations of these numerical algorithms. The slash is basically mainly the Gauss. It takes care with the Gaussian elimination, but it's like the slash takes care of all the cases you can have for the matrices A and B. Okay, so you can simply use in the computer in the MATLAB this slash commands. You supply whatever is the size of the matrix A and whatever is the size of the vector B you have. So they simply you take the slash and that will give you the solution X. Okay, and since it mostly based on as I said, Gaussian elimination or any of the direct methods, the solution does not have any mathematical error. Okay, so it might have only the round off errors. It does not have any mathematical error. All right, so I think that's enough for today. We'll start the new things in the next class now. So yes. Yeah, so that's all for today's lecture. And if you have any questions, we have a few minutes, you can ask now.